bit towards the people who have some programming experience, probably something without formal education or are new to programming, and they wish to understand the basic principles of programming. So this is kind of the very basic fundamentals, but very, very important fundamentals that will hopefully allow you to have a smooth journey afterwards. And probably if you are already having some, you have, at some distance in your programming journey, probably it can clarify some of the misconceptions that are common among very, very beginners. So that's the purpose of this talk. So please feel free to interrupt anytime and ask for some concepts, because mostly we'll talk about conceptual frameworks today, but I will have also some hands-on exercises, some hands-on examples along the way. So for the agenda for today, we will talk a little bit about something that we cannot avoid talking about. So actually, we will try to start from the beginning. And the beginning is, how can computers execute programs? So that's a very important key question, because without this, you really cannot understand really what is programming, because computers' main job is just to execute programs. So computers exist because programs exist. So there is a very strong relationship between understanding programming and understanding what computers are doing, because they will be executing the programs you are writing. So you have to know what is that computer are doing and expecting so that you can program them. We will briefly touch on the concepts of algorithms and how they differ from code. Of course, I have to repeat that many of these concepts could be very familiar to some of you, but just please bear with me. So possibly you can find something of use. If not, you can also add and correct and interrupt anytime. And thank you for your time in advance. Then we will talk about the main actually theme here is a little some terminology and very important concepts related to programming. I just selected few of the basic principles, very important fundamentals. So I hope that those are representative and those will serve the people who are coming to programming or who are just having some doubts, even if they have some experience in programming a little bit. So we will talk about the concept of layers. These are very important because we have so many levels of programming languages. So what do people mean when they talk about low-level programming languages, high-level programming languages, what levels, what layers we have, and what's the concept of translation? Probably you have heard something about compilation, interpretation. So this is all translation, and we will touch on that. Another thing, we'll talk about the concept, very basic concept of variables. This is, I'm just selected few topics, but very important one. And variables are very connected to memory. So maybe I will talk a little bit about memory. And then we'll talk about program flow control. So how you control the flow of the program, which is without any manipulation, will go from the beginning to the end. But we can control the flow. Means we can control how the programming is flowing from the start to the end in execution. And finally, I mentioned just few words about data structures. Data structures is a little bit advanced concept. Probably it is for those who have major in computer science or IT, they will have more than one subject related to data structures. But it is very key concept that I cannot, of course, avoid talking about even when the target is beginning users. So let's go in. Hopefully, find at the end we have some time for some question and answer and some comments. So the first question here is, how can computers execute programs? And the key question is, what makes a computer special? What makes a computer special? This is actually a very key question, because a computer is just, it's just a collection of electronic device. It's another electronic device. So we had many electronic devices before, even before computers exist. Of course, the technology was very primitive. People used to have vacuum tubes instead of transistors. But when we had transistors and then integrated circuits, we had a lot of electronic devices, very versatile. And our life is full of electronic devices. Probably your smartphone, for example, is full for specialized chips that is doing a lot of things, like modulation, for example. So, but the computer is different. So the computer have taken over everything. So it is dominating our modern life. It has penetrated every possible detail of our life. So what makes a computer special? Probably you can just reflect on this question for 5 seconds. I used to ask this question for students who are taking, computer architecture or computer operating systems. And most of the students, they get the answer. Probably you can think about this for a second. So the main advantages of a computer is this. It is this word. Let me just show you. Sorry. Oh, it refuses to work now. Okay. Okay, no problem. So let me just close this. Open it again. I'll be sharing some sketches for today. So I hope that it will appeal to you. And the keyword here is the computer is programmable. That's the keyword. This means it can do different things. It can do different things based on the program you feed to it. So it is not hardwired. It is not special purpose electronic device. It's not hardwired to do only a single thing like any other electronic device. So an amplifier will just amplify, a switch will just switch, and modulator will just modulate. But the computer, which is represented really by a component called processor, this is different. The processor is an electronic device that is very special because its hardwiring, its design is so that whenever the input is different, the output will be different. So you can make the computer represented by the processor, you can make the computer do different things based on different inputs. This is very key idea, and it's very strange idea for example, for electronic engineers from, for example, 60, 70 years ago. Because now, suddenly, some electronic device, it can do more than one thing based on some signals at the input. And we'll talk about the nature of these signals. So this is the key idea here. We have a computer like that, and probably if you look at this system here, at this part, the big one, if we exclude the monitor, you exclude the keyboard, you exclude the mouse, which are just input-output devices, so you will find something like here. So if you open the case of this system, this is just a case, you will find many, of course, this is a quite old image. You have here some very old, actually ancient input-output devices. But in addition to having the power supply, because this is an electronic device, it needs electricity, you will find some boards, some of the printed circuit boards, very, very big, that includes other smaller circuit boards and some other chips. For example, in this image, if you look at this part here, this is the part, this is the sockets where you plug in this part, and this part is the processor, the CPU. Probably you have seen this before. So this is very special CPU, because this CPU works like the following. If we assume that the CPU, by the way, the CPU is a historic name for the processor. In the old days, when computers used to be centrally located in some place and controlling many terminals in other rooms, the name was given. The name given to that processor was Central Processing Unit. So this name stuck. So it's okay to just follow this convention. So I will use CPU and processor interchangeably. So this CPU, if you consider CPU as a black box, what happens? You provide an input and it gives you an output. For example, you ask through some signals to do something like to add two numbers, for example. This is very basic computation. This is a computer, so we do some kind of computations. The basic computations involve calculations and involves very basic arithmetic and logic operations. So everything that the CPU can do, even if you are playing games with it, even if you are doing very heavy computation using MATLAB, for example, even if you're surfing the web, even if you are taking and editing, for example, videos, eventually the basic operations, the basic input, the basic operations that can be done by the CPU is just a few arithmetic and logic operations, and we'll have, in addition to moving data around. Probably I will talk about it a little bit more, but let's focus on the basic idea. The different input will provide different output. So what this input looks like, actually it looks like something like this. Any input to the computer, here I represent the computer by the CPU. Remember, the CPU is just the main part of the computer system. So you have a big computer system, but what they call the brain, the main part, which is doing what you see is done, is actually the processor, very small chip. All the extra parts are just utility parts. They are helpful. They are helping the processor doing its job. We need the memory because we need to keep these inputs, and we need input output because we need to communicate what is done by the computer to the humans. So we need these input output devices. But the main computer is the processor. The processor is the computer. The computer is the processor. So this input will look like something like this. Only two types of signals. We have some signals called instructions. So these are the commands, because computers are there just to perform commands. You give them commands, they perform the commands. So all this output is just the result of executing. I'm using now some terminology. I'm using the terminology. So instead of performing, I will say executing the commands. So this is the terminology used in the computer literature. So you give it some instructions. By the way, that now the signals, I will name it instructions. The commands, usually called instructions. You give it some instructions, and they execute these instructions and give you different output based on the different instructions. This is very versatile. Means one unit, one electronic device can do many things based on the instruction given to it. But you cannot do too much without data, because what's the purpose of doing instructions? What's the purpose of adding two numbers if there are no two numbers? What's the purpose of displaying something if there is nothing to display? What's the purpose of controlling something if you don't have any parameters? So you always need some kind of data. Data are the operands. They are the subject. They are the object of the operations. So in addition to instructions, you will also need data. These two types of signals are all inputs received by a processor, by the computer. Again, the processor is the computer and the computer is the processor. So the output will be result of executing these instructions in addition to the data. Data are the subject or the object for the instructions. Add two numbers, provide the data. Data is the two numbers. Display something, give me what is to display. A character, symbol, something, image, that is the data. Run or play some video, where is the video? That's the data. Display some image, where are the pixels? That's the data. So this is the gist of what computers are doing. If you look again at these instructions, it will look something like that. So now we are coming closer to the native nature of the processor as an electronic device. Electronic devices are working with electricity. Electricity, we have either voltage or currents. So if we consider just voltage as a signal, we can have something like that. One instruction could be, in addition to the data, this is either an instruction or data, I don't know. This could be an instruction, could be a data. Of course, in real world, there will be so many more signals than this, but this is for simplicity. I'm just using 4 wires. By the way, these lines here are wires. So these are wires that could be printed on some board, or could be just internally in the design of the CPU. And these are the signals. You will later see that these signals are just probably levels of voltage, because it's electricity after all. So this is the versatility of the computers. It can receive different signals, give you different output. Let's focus more on the instructions. Let's focus more on the signals here. There are many wires now. There are 8 of them. You can give these instructions to the processor and gives you different output. If you look at these combinations of signals, actually at once, 8 of them all together, which is given to the processor at any given time together, this is called one instruction. So you cannot have a command having only one level of voltage, like you give a signal here as a high voltage or a low voltage. By convention, our convention is to call, for example, this is arbitrary, but we can call it anything. So we can call the high voltage a 1, and we can call the low voltage a 0. You can call it on and off. You can call it anything you want, A and B. But by convention, we call it 1 and 0. So if you combine all the signals given to the processor at once to do something, these combinations, so you see 1 0 0 1 1 0 0 1, these are just the signals I have taken from the wires and just put them horizontally, because they are given at once to the computer at the same time. I call this an instruction or command. And one command can do very, very little. You cannot do much with one command. It's not enough, actually. Actually, one command is not enough for anything, because you will need also data to supplement this command. If you want to add, you have to provide the operands. You have to provide the two numbers to add, for example. But when you combine many commands one after another, so when you use so many instructions of this kind, probably you will have something meaningful. Probably the result of executing all of these instructions will have something meaningful. Then we can talk. So actually, a group of instructions that are very related and do one task, this is called a program. That's a program. And what you do as a programmer is just to write these kind of instructions. Don't be worried, don't worry too much, because you will not write the program in this format. This format is really scary. Actually, it is just signals of zeros and ones, and you can just, you can lose your way here. But fortunately, humans are, they are smarter than just dealing with this thing. So these signals, it has a name. This format is called the binary format, because it has only two possible values, which is 0 and 1. So this is called the binary format. But when you talk about the program and we talk about instructions, actually we talk about programming. So usually we name this program as a code. We have a name. We say this is a code, because this is just a symbolized way to communicate with the computer. So this is kind of a code. And because this is the code that is really fed to the CPU, so the CPU can deal with this one, can understand this code. This is usually called machine code or machine language. So this is the language that is understood by the computer, and that's why this is a binary format, and that's why it is called the machine language. If you want to look at a closer look at this one or zero, this is what I have said. Actually, in reality, this one or zero is just two different levels of voltage. Probably 5 voltage, probably for high level. So this is just anything close to the high, maybe close to the 5, for example, voltage, or close to 3.3 or something like that. It depends on the system. Could be called 1. Anything close to 0 voltage, low voltage, could be called 0. And why 2 levels? Actually, why we had binary in the first place? Just let me deviate a little. System that we use. For example, we are familiar with when we represent numbers, for example. Actually, if you want to represent numbers and you have binary, it's very tedious to represent numbers from 1 to 10, for example, 1 to 9, 11, 20, 100. For example, if you want to say just 1024, you will need so many bits. You will need 10 bits. By the way, the bits is the name for one binary digit. This is a binary digit. This is one signal, binary digit, binary digit. So this is a bit. So this is formed from binary and digit. You need 8. You need actually 10 bits just to represent 1024. But in decimal system, the system we are used for, our numbering system, we have only 4 digits, 1024. So the reason for that, reliability, because it's very easy for computer systems as electronic devices to distinguish between 2 levels of voltage only, instead of distinguishing between 10 different levels of voltage. That will be very tedious, very error prone. It's very difficult to really know, am I 0 or 1 or 2 or 3 or 4 or 5 or 6, 7, 8, 9, 10. But it's very easy to tell whether I am at 0 or 1. Just have a threshold. Anything below the threshold is 0. Anything above the threshold is 1. I'm deviating, but it's okay. Now, you have a lot of instructions. Actually, these instructions are not arbitrary. Okay, it's not just instructions just for the sake of concatenating instructions. These usually solve a problem. You write a program, a series of instructions to solve a problem. And when you have a problem in mind and you have a solution in response to that problem, usually you express this solution in terms of steps. So, for example, if you want even to cook something, so you have a recipe. A recipe is just a solution for this problem, and any recipe comprises many steps. And anything actually you are doing, we follow steps. Even when you graduate, you follow steps. So whenever we talk about steps, then we talk about something a computer scientist called algorithm. Actually, this word is coming from an Arabic word, from an Arabic person called Al-Khwarizmi, who talked about this. So actually, he talked in algebra. So in honor of his achievements, they named this algorithm after his name. So the algorithm is just referring to the steps of the solution. So actually, they are referring to the instructions, but in an abstract way. These are representing what you have to do one step after the other to solve your problem. So this is called an algorithm. But an algorithm is just for us. It's just for humans. This is what we understand. And when you talk about algorithm, you can sketch the steps on paper. You can actually use something called flowchart, just diagrams. You can use pseudocode. Pseudocode is something looks similar to a programming language, but it is not a programming language. It's more like an English, like a natural language. Could be in any language. But eventually, you have to remember, the computers won't understand the algorithm. We are not yet there, actually. We don't have that artificial intelligence where the computer can receive just ideas of steps from your head, and it can just implement this in its own language. You still have to translate. You still have to translate. This is called implementation. You have to translate your ideas, the steps, into code, a code, specifically something in a programming language, any programming language. So what you do actually is you have steps. You express the steps in any way you want. Maybe in pseudocode, something looks like English. Some steps you just sketch like a recipe, and then you have to implement. Implement means writing the code. You have experience. You know at least one programming language. You see the step. You translate the step into something that could be understood by the computer, specifically in a specific programming language. So you provide the code. So for example, the flowchart, if you look at this algorithm, this is an example of a flowchart. It could look like this. This is actually there is a convention. It's not also arbitrary diagrams. There are some conventions for using specific types of diagrams to represent specific types of operations or of tasks. For example, probably you will start from somewhere. You will have some step. You will take some decision, and based on the decision, you may do something. You may display something. Every kind of diagram here has special meaning. Means some of them they just perform an operation. Some of them they take a decision, make a decision. Some of them they display some input or output, receive some input or display some output, and etc. So we will not stick on here, but let's now move. Let's now move more into this step of implementation. Okay, you go from the algorithm to the code. Let's see more about this. So first thing I will talk about is the concept of layers and translation. When we talk about this is a language that the computer can understand. Okay, so computer can understand zeros and ones. Based on the different zeros and ones, it is hardwired to do something. Okay, respond somehow. Probably this thing is adding two numbers, ANDing two number. ANDing means performing AND operation. This is logic operation, or moving data around from memory to input or from CPU to memory, etc. So this is a basic operations can be done by a processor. Just moving data around, performing some arithmetic operation, performing some logic operation. Out of all these basic operations, you can see you can do everything, including drawing, playing games, calculation, surfing the web, etc. So, but this language is not convenient for people. That's tedious. That's very horrible to use just zeros and ones to talk to the computer. So usually what people do, they are always smart enough, I mean human people, to just avoid the complexity and hide the complexities and use the concept of abstraction. So always, this is always followed by people, by the way. So always you can find people doing the following. They find something very, very difficult. So they build a layer upon this and provide something which is simpler. And then they provide somehow to go from this simple representation to the complex or difficult one. This is called abstraction. So they hide the difficult details and they build something simple, and they ask somebody to do the translation. So this is very, very common in computer science. This is very, very common. So in this case, we have computers talking in this language. It's very difficult. Build a layer upon this, okay, hide this detail, and provide something simpler. For example, something like could look like this: add or move. I said we can add two numbers, arithmetic operations. We can AND two numbers, maybe this. Or we can move data around, for example. source to destination. So this representation, this is what people did actually in history. So people did this. This is called the machine language. It is the native language of the processor. The processor cannot understand anything other than this. This is, by the way, has a name called an assembly language. This is just a very basic representation, but still very difficult. Actually, it's still very tedious because it's just same like binary, same like machine language, but it has a mapping of 1-to-1. Means every combination of signals like this, every instruction in binary, it will be given a symbolic form. This is called mnemonic, symbolic form. That's it. It's just 1-to-1 mapping. So it's still difficult. So people, again, they were smart enough to build another layer, and all of these, they just called low level because it is close to the machine, and anything close to human we consider as high. Probably it's our ego, maybe, but anything related, anything close to the human is high level. Anything related or close to the machine is low level. So what happens here? They now they have hidden these details, build another layer, and now they invented something like for example, look like a print. This is very nice instruction. This is another instruction. Or maybe instead of doing this add and this stuff, they just use the thing they are used to do in basic algebra, something like that. So this is again another instruction. But this instruction is almost in the natural language of humans. And that's why it is called high level language. Example of this is an assembly, this is a machine, and this is high level language. Example of this is C language. If you hear about that, there are actually hundreds of programming languages, but that's the idea. So, but wait a minute, the C processor cannot understand this. You cannot just simply write print and expect the processor will understand you and will respond. That's not possible. So what's happening here? Actually, when you write this form, this layer, there will be something here, somebody here, actually something here that will do translation for you. So translation, it will be done for you into this layer. And then eventually there will be another layer, another translation, another step. This to move this program, this instruction from this format, which is assembly, into the native language of the CPU. So this translation is called compilation. That's why you have something called compiler. And this translation is called assembling. And that's why you have something called assembler. And eventually the CPU expects something in binary. Otherwise, it will not respond. So we have multiple levels of programming languages, low level like machine code and assembly. We have high level languages, hundreds of them, as I said. Probably the first languages in history. I'm not sure, most of you probably didn't hear about this. So we have Fortran. This is for mathematical, for engineering computations. COBOL, this is for commercial applications. It's very famous in the old days, of course. We have C language, we have BASIC, we have Pascal. Pascal was an educational language. Actually, for me, myself, started studying computer systems in 1998, 1990s, previous century. So we used to study in BASIC and Pascal. Then we moved into C++, then we moved into Java. Nowadays, many people use Python, and we have so many programming languages. We have specialized languages like PHP for web development. We have Dart for, Flutter mobile development, Swift for, your iPhone, JavaScript for web, etc. You have so many things. This should be etc. So what happens here is that when you write, just take a minute looking at this diagram. This is a very key diagram. It looks very crowded, but actually, if you figure out this, then you are already ahead of many programmers who don't notice what is happening here when they write programs. So that's very key diagram here. These are another view of the different levels of the programming languages, but in action. So what is really happening? What's the process of moving from one level to another level? This is what's happening. First, you write your program in what is called source code. So this is how you write program in a language like C. So when you write a program, actually what you do, you write text. That's very important to notice. You write just a text. So Your file is just a text file with a special extension .c. This is an example of C programming language only. So inside this file, the text file, you just have characters. It's just some characters. Okay, for those who know this stuff, this is just ASCII characters. So you just have this kind of instructions. You ask the program to reserve some memory. This is called variable for you, and you assign a value for that, 3. So this is just a variable like the mathematical variable. And then you ask the program to print something. So the processor will take this instruction and will execute that, and you will see something on the output device, could be a monitor, for example. But you write this is just a text, but this is nothing like the native language of the computer. So what's happening here? After you write this in a text file, you will have a text file with the C extension. You will run a program. This program is called a compiler. It has to be installed on your PC. It has to be installed somewhere. Otherwise, you cannot translate. You cannot translate the source code. This is called source code. So whenever we talk about source code, whenever you hear somebody talk about source code, this means the textual code which is written or readable by humans. So it is just a text file which has some natural language like programming language, readable by human. So you do translation by a program called compiler. The compiler will do compilation. This is a special name for translation from high-level language to a low-level language like assembly. Then you will have another file as a result of this operation. You will have another file, could be extension ASM. This is for assembly. So this translation will produce an assembly code, This is not source code. This is source code, but in assembly. It's usually called assembly code. But it is still not a native language. It's still not binary. It's still not nothing that the CPU can deal with. And it is a text file. It is still a text file. But then you run another program. Maybe it could be called, this is called an assembler. So the assembler is doing something called assembling. This is another kind of translation from assembly language to the actual machine language. So usually you have something as a result called an object file. This is an object file which is binary file. This is a binary, not text. So this is the machine language. This is low-level language assembly. This is high-level language. Sometimes some programs, when you run the translation, it will do these 2 steps in 1 step. So you will just get something from the source code directly as object code. Object code is a binary, but usually this object code is not enough. It is not enough to execute, to be executed. It's not executable because usually when you write a program, as I will talk maybe in 20 or 25 minutes, when you write a program, you don't write one chunk of code. You don't usually use one file only. Usually you write many pieces, because it's very difficult to tackle one problem in one program. Usually we follow what computer scientists call a divide and conquer strategy or divide and conquer approach. So usually we divide our problem into smaller problems, and instead of writing one program, we do little programs, probably many of them. So whenever you have a program to run, actually you make use of many different object codes. It's not only one. Okay. So what's the next level? The next level is to combine the object code, the binary machine code that you have written, with other object codes written probably for you, but you are using them. Probably you didn't write that, but it is there for you to use. Usually, if you hear about that, usually these are files that will reside in something called a library. So probably when you program, you will use programming libraries. You will use some files that are already written, programs already written and translated, or they're already in object code for you. You can use them. You can use whatever they can do. So what happens? There is another piece, another program in addition to the compiler, to the assembler. This is called the linker, and you do something called linking, and linking will combine all of these objects file, and the result is still a binary file, but this time it is enough for the CPU to execute. That's why it is called an executable file. So if you start with a C programming language, .c, then .asm, then .o, then you will have something called .exe. This dash for any name, some name of the file, .exe. This is executable file. And this is the file that you double click to execute, or you write on the command line and hit enter, so it will be executed. So in summary, this is a very basic principle, but if you just get this idea, that's enough from this talk. Programming is like this. You have a computer that is hardware. Computer is hardware, but the computer hardware is useless. Is useless because the only function that the computers are designed to do, are supposed to do is to execute programs. Usually programs collectively have a name called software to contrast with hardware. We have all kind of programs, whether low level or high level, we call them software. Software, you know, ware, like kitchenware. If you can't change the ware, this thing, it is hard. So like the actual chips inside the computers, they are hardware. But like programs, you can just delete them and change them and translate again and modify and install and uninstall. So it is soft. It is changeable, modifiable. So it is software. And you know that above the computer hardware, which is the main pieces of a computer hardware, is the CPU, the processor, and we need also memory and input-output devices to communicate whatever the CPU is doing to the humans. So we have these three basic levels: machine code, assembly code. These are both low-level languages. And then we have the source code in a high-level language. And then you are here happy programmer that is only dealing with source code in something readable by humans. So let's talk now, let's move into variables, the concept of variables. So that I will rush a little bit so that we have some time to see examples. So if we talk about variables, we have to talk about memory. I said previously that you need, whatever you are doing with the computer, you cannot do with only instructions. You must use data. So actually, even if you talk about instructions, where are these instructions? So CPU is a chip, it's a very small chip. Actually, you send the instructions and you send the data. So they are coming from where, really, exactly? So you need a concept of a storage system. This is the modern computer. They use, this is called stored program model of computation. Means we don't have a CPU and we don't stand on the CPU feeding the instructions and the data manually, like what it was the case in the very, very, very old days. The very, very first computers, people used to stand. Of course, the computer was in the big, very big, like the size of a room. And people used to stand in front of the computer like a switch panel, and they just change some switches and provide the instructions on the fly. That's not very nice. So people invented this model of stored program. So all the instructions and data would be stored somewhere. And this where could be like a hard disk or something else. But actually, the CPU, unfortunately, cannot talk to the hard disk, because CPU is very, very, very fast. It's totally different technology. It's electronic semiconductor technology. Hard disks are still very, very slow. They are electromechanical devices. So we have to have some device close to the CPU in terms of technology, another device, another semiconductor-based electronic device. This is called memory. And probably you know this by the name of RAM or ROM. So we need to keep our data and instructions in memory first, so the CPU can talk to that, can fetch, can bring instructions, can execute, and ask for any data if needed. So whenever you program, whenever you need some data, you have to store the data in memory, and usually you give names. You give names to those data stored in memory, and these are called variables. So this is how it looks like. Whenever you have a computer, if you look at the first diagram, you will have many pieces on a big board called motherboard. And you will have a chip for the CPU processor, and you will have other chips. For example, this board contains a lot of chips here in black. This is a memory. This is memory chips. There are lines between them. Usually it is in gold, not orange anyway. But anyway, so usually the CPU is connected to the RAM, and it can fetch the instructions and the data. And you have to define this data when you write the program. So this is what's happening conceptually. You have a CPU. It asks for instructions from the memory. And all the instructions and data, again, whatever you store in memory is in binary. Usually, we divide the memory conceptually into locations. So one location, of course, the very, very basic location is one digit, one binary. It's one kind of, signal. It's called bit. It's called a bit. But we don't use bits individually. Usually, the convention is to use the basic unit that we use between CPU and memory is something called a byte. So the byte is the smallest addressable unit in memory, which is just a collection of 8 bits. So each collection of 8 bits called the byte, it will have its own address. It will have its own identifier in RAM. So whenever you talk to that, you can use the address, but usually you don't use an address because it's very difficult to memorize addresses. Actually, I wrote this as 000, but really, this will not look like this. Really, these addresses will be, of course, in binary, and it could look something like, even in hexa, like this thing. something like that. It's very complicated. These are something like this. It's very complicated, means very long string of bits. One address. I am referring to a single address. So you don't use addresses. What do you use if you want to define, or you want to tell the computer that I'm going to use some data here, and I want that data, I want to store something here. So you need to specify the address. Where is you are referring to? Actually, you are using names. Just you are using names, and that's what's called variables in programming languages. So if you talk about assembly, you will write something like that: A, B, C. If you talk in C, for example, program, high-level language, you can use C, A, B. These C's and A's and B's are just names for locations in memory, and that's the concept of variable. So a variable will be some place in memory, which could probably be multiple bytes. For example, in C, if you use one number, you can use a number called integer. Integer is one kind of numbers you can use in your programs, and this integer, like what it looks like, it is just an integer. You cannot use fractions, you cannot use decimal point, so it's just integers. Usually when you ask the compiler to reserve some integer for you in memory, you write something like this. You write int. This is the syntax of C. I didn't choose that. So for example, you say write C. Int is a reserved word. This is a reserved word, a keyword that is understood by the compiler of the C language, and it will result in reserving some locations in memory for you to be used later on under the name of C. You may give it even a value if you want. This is just a syntax. I am writing semicolon because by syntax of the C, you have to end every statement, every line, every instruction by a semicolon. So what's happening after this instruction? This is what's happening. You will have in memory, this is in RAM, somewhere in RAM, maybe somewhere here. You will have 4 bytes. Actually, an integer in C is comprised of 4 bytes. It's not only 1 byte. 1 byte is very small. You can represent only numbers here. 1 byte, you can represent in decimal numbers from 0 to 255 only. Very, very small. But usually you have 4 bytes, and this byte will be under the same name of C, and the value inside could be 3. So that's the concept of variable, but variables could be more complex. Could be not only integers, could be numbers with floating points, decimal point. So this is called a float, just a float. It's just, I'm talking about the C programming language, or it could be a character. You can just reserve 1 byte to represent the character, but I will avoid these details because it needs more sessions. So please bear with me. But that's the idea. Instructions are coming from memory, data are coming from memory, and then we have variables. So let's talk a little bit before I move to the examples. Let's talk about flow, the control of the program flow. So actually, by default, if you are writing a program, by default, imagine these boxes. If you can see these boxes, these blocks, imagine these are different statements, different instructions. I'm using now a different terminology. Maybe it is called statement, but let's call it instructions. But it could be called statement, for example, or a command. So this statement or instruction after instruction after instruction. This is the this is an implementation of the algorithm. You have steps, and you have translated those steps into programming language. So you have many instructions. But by default, the execution will go from the beginning to the end. So you expect the CPU to fetch the first instruction, execute it, the second is executed, the third executed until the end. Not always you need this. You sometimes, many times actually, sometimes you want to change the flow of the program. You want to change the program flow. So this is called controlling the flow. Like what, for example? I will just mention a couple examples. The main actually examples of changing the flow of the control or controlling the flow, which is one is branching. Maybe at some point you want to branch. So based on something, some state here, based on some information here, you may need to execute these instructions or those instructions. So sometimes you don't want to go through the same group of instructions every time you run the program. Sometimes you run the program with some input. Another time you run the same program with another input. Based on these inputs, the state, you may have different paths, you branch to different paths. So this is called branching. And usually we use something called conditional statements, and we can go here or there. Another example of controlling the flow is looping. many times you need to repeat some instructions, like here, I move into this, then that, and that. Then I want to repeat these three instructions or statements. Of course, there will be some condition, there will be something that will stop me from repetition or that will initiate the repetition. But eventually, if I finish looping through some iterations different times, I will go out of this loop and I will continue executing the rest of the flow. So the branching I talk about could be something like that. Could be a statement called if. This is just an example of statement in a high-level language. And then some condition upon which we will base our decision to branch A, left or right. And this is just a then, this is just a keyword. You might have this or not, depends. And then you may execute these statements if the condition is true. For example, if the condition is x greater than 5, it depends. What is x? Assume x is 6. If x is 6, so 6 is greater than 5, the answer is true. This is a test. This is a question. This is so yes, 6 is greater than 5. So I will execute this. This is the branch I will take if the condition is true. Else, this is a keyword. This is a keyword. This is a keyword. Else, if that's not true, if the condition is false, I will execute these instructions or these statements. So these are just examples of the conditions you can have. Maybe you can test whether A equals to B, or whether X is greater than 5, or whether the name is ABC, etc. Last thing, let's talk also about modularity. Maybe I will show you that in the example, but you have to know this idea if you want really to be introduced to programming. Many times, actually most of the times, actually almost all of the times, because this is recommended and this is good practice. If you have a big problem, you don't tackle the big problem. You have to divide and conquer. So you have to divide the big problem into smaller problems. We write a solution for the problem in terms of a program. So again, just focus on that. Instead of a big problem, you will have a big program, but we don't want to write big programs. This is error prone and very difficult to maintain, very difficult to understand, very difficult to manage. So we divide and conquer again, and instead of having smaller problems, we have smaller programs. And these programs usually called subprograms or modules. And subprograms have different names over the history. So for example, you can have something called a subroutine. For example, this is very common in assembly language. Or you can have something called a procedure. I remember. But most commonly, this is called functions. Most commonly in C, in Python, many programming languages, JavaScript, etc. This is called a function. And based on the paradigm you are using, sometimes this is called a method. But I will not go into that because this is related to certain paradigm called OOP. So whenever you program in OOP, you will call these functions a method. But just ignore that. So these modules provide us with something called modularity. Modularity is a good feature because you now can manage different pieces of the program differently. Even different people can work on different subprograms. It's easy to fix the problems. It's easy to maintain. It's easy to modify. It's easy to add features. Last thing I want to mention today is the data structures. So you would probably have heard about data structures. Actually, I said you use variables. Okay, you use memory. You use data and you store data in memory. You store data in memory. So whatever data you use in your program, you have to store in memory, probably in something called variables. Now the question, these variables are not one just form. It's not only the same level of complexity. Some forms of data are very simple and some forms of data are very complex. Sometimes you need one piece of data like a single number. Sometimes you need a series of data like a list of numbers. For example, you want to store marks for many students, not only a single student. So this, you cannot just keep tracking individual marks for 100 or 200 or 10,000 students. Usually you can combine them somehow. And this way of combination, this way of representing data in memory, this is called the data structure. So data structure is how you represent the data in memory. And there are different ways to do that. And usually every way of representing data can have its own operations associated with it. But just to have, I am referring to this book. Please, you can Google this up later on. There is a very famous, very prominent computer scientist in the old days called Niklaus Wirth. I think he has invented the Pascal language. He wrote a book called Algorithms plus Data Structures equal Program. So that's the summary of programming. If you really, really want to be a good programmer, that's the summary. That's the final word I have here before I show you some examples. You have to know this. You have to know how to write, how to design algorithms, which is a way of thinking. So you have to think primitively like a computer system. So you have to learn how to think in a low level. And the better you are familiar with this way of thinking, then the better you can produce algorithms that work. People call this sometimes problem solving skill, critical thinking, whatever. But problem solving is the most common term. So you have to know how to think in a way that the computer can execute. And second, whenever you are coming to execute, to implement, you remember algorithm, you have algorithm, you implement, and you have code. Whenever you implement, you go here, you will have to use a lot of data. Instead of writing the instructions and memorizing the syntax of the specific language you are using, you will use a lot of data. So you will have to think in terms of data structures. The more you know about data structures, the better programmer you are. So examples of data structures is individual variables or lists of variables. This could be called an array in some programming languages, or lists, or something like this. This is, by the way, called linked lists. These are terms I'm just throwing up, but okay, don't worry if you don't get it. Just for the future, this is just some way. For example, in this case, you link each variable to another variable. So you provide a pointer from one piece of data to another piece of data because they are related together. And this array also can have very many kinds of restrictions. If I restrict that you can add only from this part and extract from this part, this is called a stack. And if I am controlling the operations, means I allow in an array, in a list, I allow data to go from here and go out, go in from here and go out from here, different directions. Then this is called a queue. So these are the names of different abstract or more concrete data structures that you will study. If you have computer science major, you will study this in more than one subject, most probably. And that's it. So let's just before the question and answer, move into just a few examples. So I will show you first very basic example to illustrate the basic idea of translation. So this is just a program I'm using. This is called text editor. Of course, you can use even text file, but I'm using, this is called Visual Studio Code. This is just one kind of text editor you can use to write programs. And a very basic program, for example, in C language, I will use C or Python. For example, let's see this program. It's a very basic program. In a C syntax, you have to use a C syntax. So this is an example of a C syntax. I hope you can see this. This is an example of a C syntax. So in C language, whatever you write, you have to write in a subprogram. At least you have to have one subprogram. You remember modularity, subprogram. This is called a function in C. And you have to use at least one function, and the name is fixed. It has to be main. Otherwise, the compiler won't understand. So this is for C language. Every language has its own conventions and its own system. So for the C, you use something called the main. This is one subprogram, and these are statements. These very basic statements. And this is implementing an algorithm for swapping two numbers. Imagine that I want to solve a problem. Very basic one. What is the problem? This problem. I have a variable. I have something called A. Just an example. I have another piece of data called B. This is a variable. By the way, this is a variable, a location in memory with a name. This is another variable, a location in memory with a name. And every variable has a value. Value is different than the name. So maybe this is 3, maybe this is 5. What if I ask you to swap? I want you to put 5 into A and put 3 into B. How can you solve this problem? So maybe I can ask you, but for shortage of time, I would just provide the analysis. Actually, you cannot do it in a straightforward way. Actually, you have to do something, because if I just move 5 into A, this will be overwritten, and I will have 5 here and here, and I will lose 3. So no more 3. So how can I later on move 3 into 5? The same also goes for B. I cannot just move 3 into B, because I will overwrite 5 and I will lose the 5. This is very similar to if you have 2 cups. This is, for example, water, and this is, for example, juice, for example. So how can you put the water in this and the juice in that? You cannot do it, actually, unless you use a third glass or cup. So you move this here first, and then you move this second here, and then you move this here. So that's the way to swap. So this is an algorithm, by the way. You notice how we thought about this? These are the steps. So if I have A and B, I have to introduce another thing called, for example, temp, for temporary. So I have to put first whatever in A inside temporary. In programming languages, this is what I am doing. This is how you write it. You say you assign A to temp. This means move whatever inside A to temp. So this is the result. Then I will move whatever in B to A. And next, I will move whatever in temp to B. That's the algorithm, and that's the implementation. So how it is written, I cannot just write those 3 instructions only in a language like C. I have to write all of these, because I first have to tell the compiler. This is called declaration. Can you see there? Ahmed, can you see the code here?
Yes, I can see. I can see
okay.
the code.
Okay, so this is a declaration. Means you declare, you tell the compiler, I need A, I need B, I need temp. These are 3 variables. From they are both integers. Of course, you can choose another type, but this is for another session. So then, yes, you can print. You can tell the user, because you expect this A, B, and temp not to be hard coded, into the program. You want the user to be able to provide the input. So probably you will use something like print, and you will ask the user to write A, and you will receive. You receive the value of A from the user. Actually, in C, I will not explain this here. It's not enough time, but in C, you write this statement. This is called scanf. So you scan some file, input stream, and you specify what type you expect. This is D for integer. And then you give the name of the variable where you expect to receive the value. So this will be in memory. And don't worry about this ampersand, because this is something called reference. This is expecting a pointer, a reference to means usually scanf expects a very specific type. So just ignore this ampersand for now. You just assume that whatever the user will put on the by a keyboard, we will scan the keyboard. We will scan whatever entered at the keyboard, and we will store it in A. Again, you ask the user again for B, and you will scan whatever the user is typing, keying in, and you will store that in B. Then you will do the 3 basic. This is actually the basic program. You will do temp equals A equals B, B equals temp. This is the same what we have done here. And then you will just print after swapping. This is the result. A becomes so and so. This is printf statement. This is actually a function. This function you didn't write. Who is sending this A and B to the screen? This will be displayed at the screen. You didn't write that. So where is the code for this printf and scanf? These are here, actually. So this is another module. We are using some object files from a library. That's why we ask the compiler to include another library, standard input-output library, because in that library, you can find the code. We tell the compiler, you can find the code for printf and scanf. Then the linker can link these codes with our code, which is this, the swap, and then we can get the result. So how to translate this program? So look what I will do. I will use a compiler. There is a compiler called DCC. This is a compiler for C language that understands the C language. And I will write the name of the source code. Remember, this is example0.c. Remember the source code. This is text file. And I can also I can suggest a name. So maybe I suggest a name, for example, my output. This is just a name arbitrary. I'm I am just inventing now. This just the name. This is the executable file, the file that is produced out of the compilation and then assembling. Then if I hit enter, this is what will happen. You see this file? I had this file here, my output executable. Of course, you cannot display this because it's binary, but I already got this executable file. Of course, there were also addition object file. If you want to see all the files that had produced, I can do the following. I can remove this file just to show you this this process. If you are interested, sorry if I will take just a few more minutes. Sorry for that. But if you are interested, I can show you this, the result of this process. So what you can do the compilation, and you can ask, is it temps? I forgot about that. Temps. You can ask the compiler to keep the temporary files. So after this command, you can see here to the left, I have example 0C, I have example 0O that I told you about object file, and I have example 0S. This is assembly. This is how assembly look like in Intel processors. And then my output exe, which is the name I have given to it. Now, how to execute this exe? I can double click, but I can write this example 0. No, sorry, it is my output. Now the name is my output. And when I hit enter, means I want to execute this. The result is A. You remember this is the program. It is asking me for A. So it is printing A. Then it is scanning my input. So I provide, for example, 3. And then it asks me for B. And I am providing the input here. It scans the terminal, and I am writing 5. Then it is calculating everything very, very fast and giving me the result. So after swapping, A equals 5 instead of 3, and B equals 3. Okay, this is a very basic example for implementing an algorithm. Let's do that in Python. I will show you that Python, why people like Python nowadays, because Python looks similar. So in Python, I can do the following. So let me just, let me remove this first. I can do the following. I can do A equals, I ask input from the user, A equals something. This is the same, but in Python language. B, instead of doing, instead of doing printf, I'm doing and scan. Instead of scan and printf, I'm doing input, and that's it. Instead of printf and scanf, printf and scanf. That's why people like Python, because its syntax is easier. Then after I received A and B, and I can do the swapping. So I don't need to declare the variables in Python. I can just use the variables, and the compiler will understand, the interpreter will understand the type. So I can just directly write temp equals A equals B, and then B equals temp without declaring them first. Then I can print. And printing is not printf. Printing is as simple as just this command, just that. So I print A equals A. This is a variable. And again, I print B. This is whatever I put into quotation marks. This will be shown as is on the screen. The compiler doesn't do anything. But the B, when I write without quotation, this will be brought from here, from whatever was entered first by the user, then swapped by the algorithm, by our code. So if I run this program now, let me just clear this. If I run this program now, that's the result. A equals, I provide 3. Sorry. Okay, let me just use. Seems okay. Let me see what I can do. Okay, maybe I can just call the program from here. So I have a program called example. Okay, probably I need to run that. Just bear with me a little bit. It seems that my Visual Studio Code is not ready to run this. I cannot provide the. It seems that I cannot provide the input. Okay. I will just avoid Visual Studio for this for now. Maybe I can use just the Python that I have on Windows, installed on Windows. So maybe I can just write the program. I will just use the interpreter from my my Windows to run the example one. So 3a is 3, b is 5, then the result is a equals 5, b equals 3. This is the same actually function as the program by the C, but it looks a little bit shorter, isn't it? So, and by the way, just a notice, if somebody is curious, in case of Python, you will not have those temporary files like object files and executable files, because I missed this point, but I cannot also explain everything. But when we do this translation, there are actually two types of translation. There is something called compilation and something called interpretation. So in compilation, which is what happens in the case of C, for example, in the compilation, if you are compiling something, you have the source file, the source code, and you compile once and you get something, the result, the object code or the executable code before executing. But in interpretation, there is something called interpretation, like what happened in the case of Python and BASIC, for example. So you provide the source code, there will be no executable file. You will just, the interpreter, which is the Python language. You remember I wrote Python in front of the line, this here, this one. So it will take the instructions one by one, and it on the fly, it will interpret, understand each instruction, and produce the output. Directly, you will get the output. Here you run, then you get the output. Here you get the output directly from interpreter. You will get the output from interpreter. This is just a quick note, just if you're curious why we didn't have those intermediary files in the case of Python. Okay, there are other examples. For example, if you are interested, maybe I will give you this. For example, if you want to see how a branching is done. So let's look at this very basic example, even odd. This is a C example again. So I have here a function again, C. This is, you have to write it in a function. You notice in the Python case, I didn't have to write function, but I can write function. I can, for example, put this. I can put this in a module, in a separate module. So I can put this in Python. We do that not using a main or using, you just write diff, like for define a function. And I can say this is swap. And I can give arguments, means usually when you call a function, you use a subprogram. Usually you provide the data for that. So swapping what? Swapping A and B, some two names. I am free to choose the names. By the syntax of Python, you have to provide a colon. Then I will provide this code. I can provide this. Oh, I lost the code. So just temp equals A equals B, and B equals temp. So this is by itself a function that does swapping for me. Then I can return. This is what you do usually. You return N and B. This is what you do after you do something with A and B. You return. Then after you receive the A and B, I will show you what's the meaning of returning a value. This is another concept I didn't explain, but of course, it's easy to understand because whenever you call a function, you ask for the help of a subprogram, you usually expect some value to be returned to you. That is as a result. So in this program, what we do, in Python, we just receive A and B. Then I will receive A, I will change the values of A and B so that they are coming from the swap function. Swap function is defined here. This is a swap function. So this swap, I provide the value of A and B. What are these A and B? This is coming from the user. This is A. This is A. This is B. This is A. This is B. So they will go from here and they will come into this swap function, and this will be performed, and this function will return this to me. I will receive the return value, which should be exchanged already. I will receive them in A and B, so I will overwrite the old values of A and B. If A and B here are 5 and 7, here will be 7 and 5, a result of swapping. So if I run this program, I'm not sure this could be run here. Again, probably I will have to save it. I may again have to go to this. So I will run the program using Python. What is the name of this program? Is even example 1 again, example 1. So now A is 7, for example, B is 88. Then the result is 88887. Remember, this is actually the result of executing this, calling a function. Now I define the function, subprogram, a small program that is doing swapping for me. Why I am doing this? Because later on, I don't have to change the program. I can change swap only, and I keep the whole program as is. So for example, if I have another idea for swapping, there is another idea. There is a trick actually for swapping instead of this. You can do the following. You can do A equals B equals A minus B. Then you can do, this is without using temporary variable. Then you can use B equals B plus A, and then A equals B minus A. So this is another way of doing the swapping without using a temporary variable. So if I store this, just to make sure that this is new, that I changed already the program. So I changed something here to see the change. Now I go to the interpreter. I say Python example1.py. .py is the extension for Python modules, for Python files. Now A equals, for example, 44, 5 equals 555. I have an error. You see, there is an error here. This is how you say you have errors in your code. I got the error codes unsupported operand types, and this is a good example. So I made a mistake here because I did operations like arithmetic operations, okay, on data type which cannot do operations. The problem here is that the input function of Python retains something like a character called a string. This is the meaning of this string. You see, string means is something, a string of characters. You don't do arithmetic operations on characters like A and B. So what I need to do, I need to convert all these input to integer using another function I will called int. Integer means this is changing whatever I receive from the keyboard. I receive 3. For Python, this 3 is a string, is a character, not a number. I will change it into a number using this int. This is called casting into this int function. So now I am receiving integers. So now if I run the program again, it should be okay. For example, 555, 666. Now it's okay. New A is 666, new B is 555. So this is illustrating two concepts. First, 3 concepts actually. First, the concept of algorithm implementation, the concept of modularity. This is a function. I just called the function. Also the parameters, and also how to fix errors. For example, one type of error is the data type. You are using some data type like strings or numbers, which are not suitable for the operation you try to perform. There are other examples, but I will skip that for the sake of time because it's already 18 minutes after 4. But just have a look if you want to examples about if branching. You can have this odd and even. So this is an example of a program in C that will receive a number, enter an integer, scan this integer. So you receive a number into something called a num. Num is a variable called int, called a num. And what you will do an if-else statement. So you will perform some operation that is understood by C called modulo. This is a remainder of division. Modulo is in the calculator. You can find it here, mode. So if this is a remainder of division. For example, if I divide 5, I write mode. You can see my screen, mode 2. 5 divided by 2 is 2, but the remainder is 1. So the remainder is 1. So the remainder of the division. You have the quotient, but you have a remainder, so this is the remainder. So whenever you take the remainder of dividing any number by 2, if the remainder is 0, means this number is divisible by 2. So this is even number. So you print this number is even. But if your number is not divisible by 2, means the remainder is not 0, it is 1, you would print this is an odd number. As simple as that. So let's run this program. First, let me translate this program. So I will write again GCC. This program is called even odd. Okay, I am translating this program. I will keep the same number, even same name. I will write O even. This is just /O -O is allowing me to give a name for the executable file, and that's it. Then I got even odd here. You can see executable file. So I will execute that using just the name of the file. So it will ask me for enter an integer. I will give 5. 5 is odd. Okay, again, if I do the same, I give, for example, 8088. This is even, so the result 8088 is even. So that's the implementation of if-else statement. And you can have other examples, like, for example, sum 4. You repeat some instructions. Usually you use 4 instructions to repeat. In this case, you repeat an addition of some numbers. For example, in this case, later on, you can have a look. Sorry for the rush. Just I want to take more time, but let's just finish with this. So if I give you 5 numbers or whatever numbers, 5, 6, you can choose. Then I will add them up. So I will perform this operation. Give me just any number, any integer, natural number, and I will add them up. So in this case, this is 6, 15. So you can choose any number. So how to implement this? I have to first use a variable called sum. First, it will be 0. Then I have to go in a loop. And each time I do sum equals sum plus some number. So each time I say, for example, I set another variable called I. First I could be 1, okay, starting from 1. Then if you give me 5, I will say while as long as x, as long as I is less than or equal to 5, you have to add I to the sum. Sum is 0 first, so it will be first 1 plus 0. Then the next time it will be 1 plus 0. You have to increment I. So you start with I equals 1. This is inside the loop. Okay, this is inside the loop. So the loop is waiting for I to be greater than 5. First, I is 1. So sum will become 1 because 0 plus 1 is 1. Next time I becomes 2. So 2 plus 1 is 3. Next time I becomes 3. So 3 plus 3 is 6. Next time, because I am adding 1 to I will become 4. So 4 plus 6 is 10. Next time I is 5. Still I is equal to greater than less than or equal to 5. So I equal 5. 5 plus 10 is 15. Next time I equals 6. But 6 is greater than of I, so the condition is not true anymore. So we will stop here. So this idea, this algorithm, it will look like this using something called a for loop in C. First, you receive the n, what integer you want up to, which integer you want to add up. Then you use a for syntax. So you specify I where it starts. This is equals 1, and sum equals 0 first. And then you repeat this until as long as, while means as long as I is less than or equal to n, 5 in this case. And each time you increment I by 1. This is a shorthand of C. In C, instead of writing this, I equals I plus 1, you can just write I plus plus. This is the syntax of C. It's nothing special. And instead of writing sum equals sum plus I, you can write sum plus equal, plus equal I. This is a shorthand for writing this in C. And this is a shorthand for writing this in C. So we write sum equals sum plus I for as long as 5 times probably. So let's run this. Let's first build this program. For example, I use GCC, and this program is called sum4. So the resulting, because I didn't specify a name, it will give it A, name of A. You can find it here because I didn't specify any name. So now I can implement A, I can execute A. So it will ask me for a positive number. If I give it 5, the result is 15. That's just the result of, sorry, where is the sum4? The result of doing all of these repetitions repeatedly. If I repeat the program with, for example, 10, so the total of the first 10 integers is 55, etc. So anyway, I will stop here. Thank you very much. Actually, I have more examples, but probably you can refer to many more examples on Google, and probably we can give you some pointers to examples. So I will give you some pointer to a lot of examples like this one, a link for specific examples in C, same like this one where I took these examples from. So I can refer you to this website. Of course, there are plenty of websites, actually hundreds of thousands. But this is one website you can find a lot of C examples. Of course, for Python, you have to look for yourself, or you can just translate in Python. But of course, after you take a course in programming. So I hope that this is giving you a very quick summary of the most basic concepts of programming, including the things we talked about today, which is how programs are executed by CPU, what is the notion of instructions, and the different levels of programs, low level and high level, and the layers and the translation that's happening between the layers, and also some concepts like the variables, which are some data you keep in memory, and some way of controlling the flow of a program, and also finally the concept of modularity and data structures. I will stop by here. Apologize really for taking too much time, 26 minutes more than before. Thank you very much for bearing with me until this time, and now the stage is open for any corrections or additions, and or any question if there is some. Then we can end the day. Thank you very much. Is there any addition or correction or any request for clarification? I guess it was a very quick tour. So probably for the beginners, probably the students who are taking programming, maybe you can have another look at the slides. We'll share the slides on Facebook, and a recording of this video will be shared also on the YouTube channel of TES, the Energy Sphere. So probably you can have a look at the slides and maybe Google up some, and probably later on, if you have some questions, you can post them on the channel. We have actually a Teams channel on Microsoft Teams. There is a group, there's a team actually set up for this series. So probably if you provide your email, you can join this team and you can also participate later on. Is that okay, Ahmed? I think there is no question, so can you follow me?
Okay. Yeah, I think I will, what do you call this? Have people, I will invite people to join our teams so that we can have a,
Okay. Yeah. Very good. Actually, yeah, especially who is interested in joining the channel, they can, so they can even ask questions offline. But yeah, that's it for today then. Thank you very much, really. Thank you very much. I appreciate your time. Thank you very much for joining us. And for those who are already know this stuff, I apologize, but I thank you for their support. And for the people who are just beginning their journey, I hope that these are very quick pointers that can be of use for you. And I invite you also to the next month. We'll have also a couple of talks again for technical and coffee hour. So we will be, it will be our pleasure to also join us again. So for today, I think if there is nothing else, we will call it a day, and we will thank you again, and we will just end the Teams meeting soon. Thank you, guys. See you, and Assalamu alaikum and good afternoon.
Waalaikumsalam warahmatullah. Thank you, Dr.